Welcome everyone. It's a great pleasure to have here Colin Hill today. Thanks a lot for accepting our invitation. Colin joined the Columbia University Physics Department as an assistant professor in August 2019. He received a PhD in astrophysical sciences from Princeton University, following undergraduate and master's degree at MIT and Cambridge University, respectively. He was a junior fellow in the Simons Society of Fellows, hosted at Columbia, and a postdoctoral member at the Institute for Advanced Study. Finally, he held a joint position as an associate research scientist at the Center for Computational Astrophysics at the Flatiron Institute. Today, he will present Uncovering Physics Beyond the Standard Model in the Primary and Secondary CMB Anisotropies. Colin, please, you can start when you're ready.
Okay, great. Thanks, Leonora, and thanks a lot for the invitation. Okay, so this talk is going to be comprised of two parts, as the title suggests. The first part is going to be about the primary CMB, and that's really going to be telling a story about the recent Atacama Cosmology Telescope results, which are in this set of 4 papers here listed on the right side of the screen. And then the second part of the talk, we'll discuss some other work led by Sam Goldstein, my student at Columbia, and Fiona McCarthy, who was a postdoc at CCA and now a postdoc at Cambridge. And that will concern new physics in the CMB secondary anisotropies. So the reason to split it up is that I know that probably some of you have already heard a reasonable amount about the ACT results, and so I'd like to make sure that I cover some other material as well. But if you haven't heard about ACT, I will try to make sure to give you a pretty reasonable coverage of what we found earlier this year. Okay, so that's the outline. And at the end, I'll say a few words about the current status of the Simons Observatory and give you a little taste of some of the actual data that we've started to take with that instrument. Okay, so let's dive right in. I'm going to start with the ACT DR6 results. I want to emphasize that this is really the effort of many, many dozens and dozens of people going the whole way back to the beginning of the ACT experiment almost 20 years ago. But some of the key people involved, including some of the folks at Columbia who worked on this with me, are down here on the bottom left. Okay, so first let me give you a rundown about ACT, both the instrument and then the maps comprising our data release 6 data set. Okay, so ACT was a 6-meter CMB telescope located in the Atacama Desert, as the name would suggest. That's up here in northern Chile. The reason this site is so good for millimeter wave astronomy is that it's very high and dry. It's at 5,200 meters altitude. So the water vapor content of the atmosphere is very low. The PWV is about 1 millimeter. And the nice thing about being in Chile is that because the sky rotates, you can get very large sky coverage from the ground, in contrast to the South Pole, for example. So our data release 6 data set comprises observations that were taken during the final 5 to 6 years of the observations with ACT. And the reason for that is that we had the most sensitive detector arrays on the telescope during that era. So we have previous data that came out in our earlier data releases, but DR6 was really substantially more sensitive than anything we had done before. The data came out publicly back in March, and I know many of you have had a chance to start working with it. And if you have questions, please always feel free to reach out to any of us from ACT. Okay, so here's what the instrument looked like in the DR6 era. We had these 3 detector arrays in the telescope: polarized array 4, 5, and 6. These contained a few thousand detectors, cooled to almost absolute zero. Just to give you a sense of the scale, the number of detectors that we currently have fielded in the Simons Observatory is about an order of magnitude larger than this. So ACT was great, but we've, in the past few years, scaled up to much larger instruments. We covered 3 main frequency channels in the ACT DR6 data set, centered in these bands centered at 90, 150, and 220 gigahertz. And because of the 6-meter primary dish, we have roughly arc-minute resolution at CMB frequencies. So the actual telescope is here in this picture in the bottom left. The object around the telescope is a ground screen that helps to shield the telescope from thermal emission from the surroundings. Okay, so then here's what our sky coverage looked like with ACT DR6. As I mentioned, from Chile, you can cover these very large sky areas, and so that was what we tried to do with these sensitive detector arrays. So the total sky coverage of the yellow region here, which is ACT, is about 45% of the sky. Again, because of the location in Chile, we have very nice overlap with other surveys that you know and love, like the Dark Energy Survey in red. DESI is here in green, and then the current Euclid footprints are in blue. On this essentially entire footprint, we have lower noise than Planck. For those who are CMB aficionados, our median depth is around 10 microkelvin arc minute, which is about 2.5 times better than Planck. And in polarization, we're actually closer to 3 times better than Planck, because Planck was not an ideal polarized instrument. Of course, we cover some chunks of the galaxy. As you can see in the background image here, this is dust emission from our galaxy. So for the power spectrum analysis that I'll show you, we're going to mask out the most contaminated parts and leave about 10,000 square degrees, roughly a quarter of the sky for the power spectrum estimate. Okay, it's fun to take a look at the actual maps rather than looking at the statistics, which we'll do in a minute. So here's a first taste of that. So this is Planck first. This is a Planck map at 143 gigahertz in temperature, zoomed into a region that's about 91 square degrees. And what I'm going to do then is to add in the ACT data. Sigurd Ness really did some amazing work putting this together for ACT. We're going to add in the ACT data, and what you should see is that the small scale features of the CMB are just going to pop into focus. So there we go. Hopefully this is flipping on your screen as well. So you can see once we add in the ACT data, these bright point sources that become resolved. You can even see nearby galaxies. This is the Sculptor galaxy. And then of course the CMB fluctuations themselves are also really resolved in very fine-grained focus. We have 3 frequency channels, so you can actually synthesize a multi-frequency image with different colors mapped to each frequency. So here's an example of doing that with 90 gigahertz mapped to red, 150 to green, and 220 gigahertz to blue. And in the units that we use, as some of you probably know, the CMB thermodynamic temperature units, the CMB signal is constant as a function of frequency, so it looks gray. So the fact that this image looks gray is a good sign. That tells you that it's dominated by the cosmic microwave background. But you can see these very beautiful astronomical sources that are not following the CMB blackbody frequency dependence. So for example, the blue blobs here, this is thermal dust emission from nearby galaxies like Sculptor. The red compact dots, those are AGNs or quasars, what we're seeing in synchrotron emission. And then you can see some thermal SZ galaxy clusters with their characteristic SED, which are circled in yellow. So there's a lot of beautiful multi-wavelength science that you can do with this data set. I'm not going to talk about that in too much detail today. I'm going to focus predominantly on the CMB. But I encourage you to download the maps and have fun with them. Okay, so then the last example of the maps I want to show you is in polarization. So this is where we're going to see some really incredible gains in sensitivity. So this is another small patch of sky. First from Planck. This is now looking at the E mode polarization of the CMB. This should just look like noise to you because essentially it is. Planck was an amazing instrument, but it's not cosmic variance limited in polarization on basically any scales. And so then here's what this looks like when I add in the ACT data. So this is now a signal dominated E mode map. If I flip back and forth, it's a really sensational improvement. If you look closely, you could see some correspondence of some spots, but really this is dominated in the information content by the ACT data. So this is now a signal dominated map of the E mode sky, which gives us a second tracer of the early universe that we can use to study cosmology. If I zoom back out, here's what this looks like on the full footprint. So we have a high signal to noise ratio map of the E mode polarization covering almost half the sky. And there's also observations that hit the galaxy, which you can use to study properties of the dust in our galaxy. There's some papers we've written on the galactic center, but I'm going to focus on the extragalactic cosmological patch here today. Okay, so then let me dive into the power spectra. So I'm going to zoom through many years of hard work, in particular, many thousands of null tests that Thibault Louis, Adrian Laposte, and others did incredible work doing. So these are null tests in which you split the data according to sensitivity to some systematic effect, and then you demand that the difference power spectra that you measure after doing that is consistent with null. And with the error bars as small as they are from ACT, and getting all those null tests to pass, understanding very subtle systematic effects is a huge amount of work. After we finally got there, we opened the box to look at the power spectra, the signal power spectra, and the cosmological parameters in April of 2024. So here's what we saw. I'm going to show you a few plots now that are the angular power spectra. First with Planck shown in orange, and then with the ACT data in blue. So first up is the temperature power spectrum. So this is the Planck TT power spectrum, really beautiful measurement out to L of, say, 2000 or 2500. And then here's the new ACT DR6 power spectra in blue. So what you can see is that on the range over which we overlap in terms of our angular scale coverage, that ACT and Planck agree very, very well. But the nice, impressive thing with ACT is that you can extend this measurement to the TT power spectrum out to much, much smaller angular scales. They are, however, complementary data sets. So if you're eagle-eyed, you'll notice that down here at low L, I've truncated the ACT power spectrum, even though the error bars have not started to blow up yet. And the reason for that is that we have atmospheric noise that makes the ground-based data complex to interpret and also noisy on large angular scales. So we have to measure a transfer function that represents any potential bias between our maps and the true sky. And we push this measurement down to the lowest scale, largest angular scale, where we believe that the transfer function is well calibrated. So on these largest angular scales, the satellite-based data from Planck and WMAP will remain extremely important, particularly in temperature for the foreseeable future. So very complementary in that sense. Okay, then let's turn to the polarization. So here's the Planck E-mode power spectrum, where now you can really see the noise kicking in. Very nice measurement on large scales, but then getting quite noisy as you go out to L of a few thousand. And then here's the ACT DR6 measurements in blue. So again, you can see excellent agreement between ACT and Planck on the region in which they overlap. But then with ACT, you have these sensational measurements of the E-mode power spectrum all the way out to very high L. So in terms of the sensitivity, ACT is actually more sensitive than Planck in E-modes on the entire range of angular scales that we cover with our data set. Okay, and then here's the TE power spectrum. So again, Planck in orange, and then here are the ACT measurements in blue. So there's excellent agreement between these where they overlap, and then ACT lets us measure this all the way up to essentially where it starts to go to zero. If you want to play devil's advocate, you might have said, well, the CMB measurements in temperature have complicated foregrounds, particularly on small scales where there's lots of components. So maybe we have to be worried about the cosmology that you extract from that. Well, if you want to then say, let me focus only on polarization, the TE power spectrum is now measured at such high signal to noise that you could fit the lambda CDM parameters just from this one power spectrum I'm showing you and get a 1% measurement of H naught. And a spoiler alert is that the value you get for H naught comes in around 67. So it's a low value, so to speak. Okay, so going into some of the details a little bit more. So you might wonder, when I showed you these power spectra, how is it that you're only seeing the CMB when I showed you maps earlier that had other components besides the CMB in them? And sure enough, if you look at the multi-frequency power spectra, you can see those components popping up. So this is a plot now where I show the TT power spectrum measured with the auto and cross frequencies of all our three frequency channels in ACT. So when you look at this, if you see the data points agreeing, that's telling you that the component that you're seeing has the same SED at all frequencies. So that's the cosmic microwave background. So these are ranges of angular scales where we're dominated by the CMB. But as you go to small scales, you can see a very strong frequency dependence in these power spectra. And that's telling you that these non-black body components are dominating the sky out there. So we have to develop detailed models to fit those components. In the interest of time, I'm not going to go into that in detail, but we wrote an entire 50 some odd page paper about this that you can read. So in temperature, the model that we develop has a total of 10 free parameters. This involves fitting components like the thermal Z power spectrum, the cosmic infrared background power spectra, radio source power spectra, etc. The sky is much simpler in polarization. So in TE and EE, we just have two free parameters, one for galactic dust and one for small scale Poisson point sources. In terms of any new developments in this compared to previous ACT and Planck studies, one of the things that we found we have to model in order to describe our data at with sufficient robustness is the shape of the thermal Z power spectrum. So this is also a very interesting cosmological observable, but I'm not going to have time to talk about it today. So for the first time, we're now constraining the shape, the L dependence of the thermal Z power spectrum. at of order a few sigma sensitivity. Okay, so we developed this multi-component model that describes the multi-frequency power spectra. We then fit the parameters that describe the foregrounds and the CMB, i.e. the cosmological parameters, simultaneously. You can download our likelihood from Lambda or from GitHub if you want to run the likelihood yourself. And now I'm going to go into what we found when we actually fit the power spectra with these models. So the first thing to look at is Lambda CDM. When we opened the box, we discovered that Lambda CDM provides a very good fit to our power spectra, and it also provides an excellent fit to a joint combination of the Planck and ACT power spectra. So what I'm showing you here in gray is the best fit joint Lambda CDM model to Planck plus ACT. The exact way we combine ACT and Planck here involves keeping all of the ACT data and then dropping off the Planck data points to avoid overlaps so that we don't have to worry about the covariance. Doing that more optimally is something that would be interesting to try to do, but we did not try to do that in the DR6 papers. But you can see by eye when you look at the residuals that the Lambda CDM model here that we're fitting indeed describes the data well, and if you want the exact chi-squared, it's down here in the bottom right. Okay, then here's TE. So similarly, Lambda CDM provides an excellent fit to the data. And then similarly for EE, I think here, the impressive small error bars from ACT are very apparent in the residuals. So across the entire range of angular scales here, where we're really probing totally new regime above L of 1,000 or so with the ACT data, you can see that Lambda CDM continues to provide an excellent fit. Okay, so then from there you can start to ask the question about what the parameter constraints themselves look like. So given that we found that there is a Lambda CDM model that describes both Planck and ACT acceptably well, you can then compare the parameters that are constrained from that, both individually from each data set and then from the combination of them. So first, here's a comparison of the ACT and Planck Lambda CDM parameter constraints from each data set separately. ACT is in blue, Planck is in orange. I'm only showing the 4 parameters of the Lambda CDM model that ACT really constrains independently of Planck. So the overall normalization of our spectrum, which then propagates to AS, that does involve a cross calibration to Planck, and so that's not totally independent. And then tau, the optical depth, is not measured from small scale CMB data, so that's also not part of the ACT constraining power. But if you look at these 4, so baryon density, dark matter density, the scalar spectral index, and the Hubble constant, you can see that there's excellent agreement, formally at about the 1.6 sigma level between these 2 experiments. Okay, then an interesting test you can do further is to ask, does the Lambda CDM model that's fit to this primary CMB data accurately describe what you actually measure in the low redshift universe? So here are 2 examples of that. So on the left, I'm showing the CMB lensing power spectrum. So this is the angular power spectrum of the CMB lensing potential that you reconstruct from the 4-point function of the CMB. The orange and blue dashed curves in this plot are not fits to the data. Those are actually just the ab initio prediction from Lambda CDM fit to the Planck CMB or PACT CMB data. And if you then compare to the actual measurements from ACT or Planck for CMB lensing, you can see that the agreement is really impressive. A similar test is done on the right here with the DESI BAO distance redshift relation. This is DESI DR1. I'll come back to show you some DESI DR2 results later in the talk. But with DESI DR1, the prediction is still statistically acceptable. The PTE values here are certainly not something that you would say there's a strong problem with. There's just this one outlying point that lies a bit low. And so then, given that the early universe Lambda CDM model extrapolated to low redshifts indeed matches these data well, you can furthermore combine them, and that gives you the purple curves shown on these plots. I think this is a very impressive, consistency test or end-to-end test of our understanding of the universe. We're going from 380,000 years after the Big Bang to describing stuff, within the last billion years or 2, and it agrees quite well. Okay, so then combining them all together gives us what I'm going to call PACT LB. So L stands for CMB lensing, and then DESI DR1 BAO is the B for BAO. And here are what the constraints on Lambda CDM look like when you do that. Again, focusing on the few parameters that we constrain directly with ACT. So the final result for H naught that you get in that fit comes around 68.2 plus or minus 0.36. And one fun thing to remind people, if you're giving a general talk about this, is that the preference for the existence of dark matter in this fit is enormous, right? We constrain the non-baryonic component of the clustering part of the energy density to exist at 130 sigma. So it's a pretty robust detection. All right, so now let me move on to some beyond lambda CDM models. This paper that we wrote describing extended models is very long. We covered something like 30 different models, and I'm just going to show you a small sampling of them here. If I don't cover your favorite theory model, it may well be in the paper, so please take a look at that. All right, I'm going to go roughly in order of redshift from the high redshifts, early universe, to the low redshifts today. So first, let's take a look at some inflationary physics. So we looked at constraining the primordial power spectrum. So these first results here, this is just in the context of lambda CDM. So for the first time, you can actually constrain NS robustly with an error bar comparable to Planck without using any Planck data at all. So this is WMAP plus ACT. And you can see the value of NS that we infer is in really spectacular agreement and almost the same error bar. So this confirms the deviation from a scale invariant spectrum at 7 sigma without using any Planck data. So this is, I would say, very robustly confirmed. You can then look at the so-called inflationary zoo plot. So this is a plot where the x-axis is the value of NS, and then the y-axis is the value of the tensor to scalar ratio R. We don't constrain R directly from ACT because we don't measure large enough angular scales. So the constraint on R here is dominated by the information from bicep Keck. So this is the BK18 likelihood. Good. So then the different colors here correspond to adding in, progressively additional data sets, and then the different points here correspond to different inflationary models. So power law models, or down here, this is the Starobinski R squared model. So one thing that has attracted some attention in the literature is the fact that the Starobinski model here has moved outside of the 2 sigma 95% confidence contours. So I show also a constraint here with the DESI DR2 data added, which is the green. So this is Planck plus ACT plus lensing plus DESI DR2 plus bicep Keck. And you can see that indeed it is a bit outside the 95% interval. This isn't like a 5 sigma exclusion, so to me it's not highly significant, but it's perhaps interesting, and it really does point out that NS still plays a very, very important role in determining the constraints on inflationary models from CMB. So this is exciting because we're going to continue to improve NS substantially in the coming years with Simons Observatory. Okay, one can then go beyond the power law form of the primordial power spectrum. So here's what it looks like if you allow running of the spectral index, so the next order correction in a logarithmic expansion of P of k. We don't detect running of the spectral index, so the resulting power spectrum is still consistent with the power law of lambda CDM, which is the dashed black line. We do tighten up the constraints on running by about 30% compared to previous data. We also looked at other extensions like allowing isocurvature perturbations in the early universe, and we did not detect any such deviations. We do significantly tighten the constraints on small scale isocurvature perturbations. So please take a look at the paper if you're interested in that. Okay, so moving down a lower in redshift, here are some constraints on extensions to lambda CDM that involve new physics around the recombination epoch. So the benchmark model in this class is a model with additional free streaming light relativistic particles, so like standard model neutrinos, but some other additional dark sector particles. So we tighten up the constraints on this NF parameter that quantifies the existence of such radiation by a substantial amount, by about a factor of 1.6 compared to the pre-ACT data. This is the posterior on this NF parameter. So orange is the pre-ACT data, and then purple is what happens when you add in ACT DR6. So the final result comes in at about 2.86 plus or minus 0.13. The standard model value here in the dashed vertical line is 3.044, corresponding to the 3 standard model neutrinos. So it fluctuates a little bit low, but it's still consistent with the standard model at a reasonable significance. And if you then furthermore add in BBN data, positing that NF should be the same at BBN and at recombination, then this tightens up by another 20% or so. As a consequence of the fact that it fluctuates a little bit low, you rule out the possible existence of additional light species at higher significance than like a Fisher forecast would suggest. So, for example, a spin 3/2 fermion that was ever in thermal contact with a primordial plasma is ruled out at about 99% confidence. So this is, I think, a pretty impressive step forward. We also looked at a twist on this scenario where instead of the new light particles being free streaming, one allows them to have very strong self-interactions. So this is quantified by this NIDR parameter. The fiducial value of this is 0 because there's no such species in the standard model. And we tighten up the bound on this parameter by about a factor of 3 compared to pre-ACT data. So this class of models with strongly self-interacting dark radiation was, I would say, one of the main contenders in my view in the Hubble tension story, and this constraint really excludes that class of models as a result, as a possible resolution of the H-naught tension. Okay, I'm not going to go into too much detail on these other models, but we looked at things like self-interactions between the standard model neutrinos or interactions between the dark matter and these forms of dark radiation, and did not detect any such extensions. We also studied constraints on the sum of the neutrino masses from the standard free streaming effects. Our constraint on this is dominated by data that are not the new ACT DR6 primary CMB results. So we find a result that's consistent with existing studies, basically Planck and DESI, plus CMB lensing from ACT and Planck dominate this constraint of 0.08 electron volts. All right, let me turn to a couple of classes of models that are of interest in the Hubble situation. So the first one I'm going to look at is this early dark energy scenario. So if you haven't heard about this, a very brief intro is that one posits the existence of some new pseudo-scalar field, which is tuned in such a way that it becomes unfrozen on its potential just before recombination. So the canonical type of potential here is this 1 minus cosine of phi to the n. If n equals 1, this would be an axion. For various reasons, the standard axion approach here does not work for trying to ameliorate the Hubble tension. So one takes n equals 2 or n equals 3 usually in these scenarios. So the field's frozen due to Hubble friction on its potential. It then starts to roll when Hubble drops below the mass of the field and then oscillates around the minimum. And eventually it will redshift away as a consequence of that. So we parameterize the model with 3 free parameters that are motivated by this type of plot. So this is showing the fractional contribution of this early dark energy to the total cosmic energy budget as a function of redshift. And the black curve here is for a canonical Hubble tension resolving model. So in these types of scenarios, you have about 10% of the energy budget stored in this EDE field at redshifts order a few thousand. So it'd be a very substantial revision to our picture of the early universe if confirmed. So the peak of this plot we define to be this parameter FEDE. The redshift where that peak is reached is defined to be this critical redshift ZC, and then the final third parameter is just the initial starting position of the field on the potential. So this is now a 3-parameter extension of lambda CDM in contrast to the 1-parameter extensions that I showed you earlier. Okay, so in one slide, here's a summary of the results on this class of models. So these are the posteriors on a subset of the parameters of interest, where this FEDE parameter in the bottom is the one that controls really the amplitude of this new contribution. You can see that in all the different cases shown here, this posterior peaks at 0. So we're not seeing any evidence coming in from the ACT data or combined with these other data sets for this new stuff. We had seen a moderate hint in our previous ACT DR4 data at about 2.5 sigma. That appears to have been a fluctuation. We also think that some improvements to our treatment of the beam leakage from temperature to polarization in DR6 might have also played a small role in the moderate shift that's seen here. If you don't believe in Bayesian statistics, you could do a frequentist model comparison. So if you just look at the best fit model in lambda CDM compared to the best fit model with the 3 additional EDE parameters, Then you can compare the chi-squared of those best fit models. The maximum improvement that we see is delta chi-squared of about 7, which if you convert to Gaussian sigmas with Wilks' theorem is a 1.7 sigma shift. So this is, there's no significant evidence. Dennis Overby summarized this as our results ruling out this idea. I wouldn't say that it's totally ruled out, but in the sense that these posteriors contain, a non-zero area that still has support, but we're not seeing any evidence of the component appearing. So I think it still remains interesting to continue to probe this class of models with the upcoming CMB data. Maybe there is something hiding out there in the high-L polarization, but we're not seeing it pop up so far. Okay, another class of models that's interesting in the H-naught situation are these models where you modify the dynamics of recombination. So there's a lot of different ways to do this. For example, with primordial magnetic fields, you can allow the fundamental constants of nature to vary, like the fine structure constant, or you can mess around with the photon sector somehow. We looked at all those types of models in detail specifically, but I'm going to show you here an example of a more model-independent way to approach this. So in this approach, which was originally developed from Lloyd Knox's group, one reconstructs the recombination history, basically the ionization fraction, as a function of redshift around recombination. So I'm showing you here some plots that compare the constraints on this reconstruction of Xe of z. First from the pre-ACT data dominated by Planck, which is shown here in orange. And then here is what you get when you add in the ACT DR6 data. So you can see that particularly on the high redshift end, really the beginning of recombination, you tighten up the constraints substantially, and that's coming from the small scale properties of the ACT data. And what we find is that the resulting history is very consistent with the standard recombination history, which is the black dashed curve. So we're not seeing some evidence of early recombination that's popping up here. That then propagates to tightening up the constraints on H-naught in these kind of models. So here's the posterior on H-naught, including results with the DESI DR2 data, which are the dashed blue. So there's, you're allowed to move things up a little bit here, but there's no long tail that runs up to very high values of H-naught. And we don't see a detection, away from the lambda CDM bound here. Okay, so let me then summarize. So this is a plot that then pulls together our constraints on H-naught first in lambda CDM up here in black, and then in a variety of extended models that are listed here in the whisker plot. So ranging from these early time modifications that I talked about a little bit to things like ineffective and down to late time modifications with the dark energy equation of state. And then I'm comparing these fits, which are all to large-scale cosmological data, to the direct measurements of H-naught in the local universe with the distance ladder from Shoes in gray or from CCHP in orange. And what you see is that in none of these extended models do we see a sufficiently significant shift to restore concordance with the Shoes H-naught measurement. There's still wiggle room available. The error bars are not infinitesimally small, so it's going to be interesting to continue to probe these scenarios and/or new scenarios with the upcoming CMB data. But for the time being, we're not seeing some smoking gun here that's pointing towards reconciling the H-naught values. So in my opinion, it seems that we're in a situation to go back to the theory drawing board at the moment. Was there a question in the chat? The distance network. Yeah, thanks, Adam. Yeah, this plot was from our DR6 paper, which predates the distance network paper. But yeah, hopefully this sort of makes the qualitative takeaway clear. Okay, so then let me say a few things about DESI and dark energy. So the day after we released our ACT DR6 results back in March, the DESI DR2 results came out. Of course, all of us have been very excited about that situation. So we've then looked at doing a few updated analyses in the months after DR6 to put things in context. So one of the interesting things is that if you, again, do this exercise of fitting the lambda CDM model to the CMB data, so this is p-act, and then predict what the distance redshift relation should be at low redshifts, you actually find pretty good agreement with the DESI DR2 results. So the orange here is if you do this exercise fitting to just Planck CMB. The blue is if you do fitting to p-act. And you can see that the PTE value, once you add in the ACT data, starts to look fine. With Planck, this 1% is the famous, 2.5 sigma discrepancy in lambda CDM between Planck and DESI. And then if you do a joint fit, including DESI, then you get the purple curve. So based on P-act here, you wouldn't say there's a big problem. And if you want to know why, it's pretty simple to see, actually. So it comes down to the value of omega m. So this is just a zoom into the 2D posterior on omega m and omega bh squared in a fit of lambda CDM to these CMB data sets. So ACT in blue, this truncated version of Planck that we use in P-act is in orange, and then the combination is in purple. And so what happens is in this multidimensional parameter space, when you combine the data, you actually get a lower value of omega m in the purple case than you get from either of the two other data sets on their own. And that lower value of omega m is in better concordance with the DESI measurements. So that's why you got this better consistency. If you then propagate that to the W0 WA constraints on evolving dark energy, then it does move it back towards lambda. So what we stated in our paper is that any hints of non-standard evolution for W0 WA are really driven by the low redshift data. So this is a plot that shows you the constraints on W0 WA from combinations that now include P-act LB, then adding in Pantheon plus supernovae, and then these other two combinations here are replacing DESI DR1 BAO with the DR2 BAO. So, in these fits, there's not a detection of evolving dark energy. These are consistent with lambda at a 2.5 sigma level. There's also been some interesting points, papers pointing out that there's kind of a single point failure in these joint fits at the moment, which is the value of tau, which comes fundamentally from the low LEE likelihoods from Planck, the latest of which is this S-roll2 likelihood that we used in the ACT DR6 work. So if you just discard the low LEE data, then what you find is that the joint fit prefers a higher value of tau. So tau moves up by something like 2 to 3 sigma. And that then, through a variety of parameter degeneracies, allows omega m to come down a bit in the joint fit. And then the lambda CDM limit here is now within the 2 sigma contours. So it's very possible that tau is, at the end of the day, kind of responsible for these mild anomalies that we're seeing. Okay, that was the last thing I wanted to say about ACT. So maybe I'll just pause and see if there's any questions before I move on. Okay. Again, if I didn't say anything about your favorite new physics model, please take a look at our paper, which has a very exhaustive deep dive into all sorts of beyond lambda CDM constraints.
Sorry.
Okay, and the second, yeah, sorry.
Couple of hands. Adam?
Yeah, Colin, just a quick question. In that scenario where tau goes up and
Yeah.
omega matter goes down, usually omega matter and H go opposite. Do you know what happens to H?
Oh, that's a good question. I think that it does go down a little bit. So the Hubble tension certainly is not ameliorated by this. So I think that the tau story very much could explain what's going on with evolving dark energy
Wait,
and with.
sorry. Wait, shouldn't H not go up? Because you said omega matter goes down and omega mH squared is usually quite fixed.
Oh, that's right. That's fixed by the CMB. Yeah, that's a good question. I don't remember off the top of my head. I don't think that it moves substantially when we looked at
Okay.
this, but I'd have to go back and check.
Okay.
Yeah, but yeah, so this tau situation, I think what it could reconcile is really the evolving dark energy and also things like this negative neutrino mass situation. I think that those are pretty much handled by this. The H naught situation is not though.
Thank you. And Fodis?
Hi, thanks for the talk. It was very enlightening. You
Oh
said
yeah, there's
something
still some
about...
more to come though.
Okay, nice, nice. You said something about detection of dark matter. As far as I understand, we don't speak about detection of dark matter. We just fit the lambda CDM in particular, a model on the data, and then we find that we need a component that behaves as dark matter with W equals 0 and also clustering at low scales. So I'm wondering if my understanding is correct.
Yeah, what we're saying here is that you need to have a component in the universe that gravitates like normal matter, that has very low pressure, is cold, and that is not coupled to the photons. So the crucial element is that it needs to have started to undergo gravitational collapse before recombination. Otherwise, you don't match the properties of the CMB at all, and also you can't match the growth of structure at lower redshifts as well. So it's very rigorously now, by many different analyses, detected that there's a component in the universe that had already started gravitationally collapsing prior to recombination and is not coupled to the photons.
Okay, okay.
And that's what we call dark matter.
But in principle, we can have this from a modified gravity or from whatever particle source. We don't need to. We can't speak about a detection. It's not a direct detection. It's an indirect.
I haven't seen a modified gravity scenario that could do this. For example, if you
Me
have a
too.
modified gravity
Me too.
scenario, you have to somehow explain why the matter power spectrum doesn't show order unity baryon acoustic oscillations, right? So if there's no dark matter, there's only baryons, then all of the matter is coupled to the photons. So the baryon acoustic oscillations and the resulting density field should be order unity features, but they're not. They're very small wiggles.
I agree, but assume that we have a effective equation of state parameter coming from modified gravity or whatever reason we would like to assume that behaves at some part of a cosmic history as matter becomes zero or radiation or whatever. But okay, thanks for the time. I think I spoke a lot.
I think it's worth exploring all these kind of possibilities. I know there has been a lot of exploration of such modified gravity scenarios, but I haven't yet seen something that seems that it can actually match the data successfully. Okay. Good. Was there any other questions? Sorry, I can't see the hands. Okay. All right, so in the final chunk of the talk, and I'll go through some of this a little quickly, I want to talk about a different line of work, which is described in these two PRL papers led by Fiona and Sam, where we're looking for signatures of new physics in secondary CMB anisotropies. So by secondary anisotropies, I mean anisotropies induced in CMB maps by processes that occur as the CMB photons propagate through the universe. So not anisotropies imprinted at recombination. So there's ones that we've already discussed a bit, particularly gravitational lensing of the CMB. There's also effects related to the evolution of gravitational potentials at late time, like the ISW effect. But the ones I'm going to focus on are scattering. Well, in our case, not exactly scattering, but effects that come from interactions between CMB photons and stuff in the universe at low redshifts. So the famous examples here are the thermal and kinematic Z effects that come from scattering off of hot electrons or electrons with a bulk momentum. But here I'm going to talk about some beyond standard model processes that could exist that would allow the CMB photons to convert into new dark states as they travel through the universe. So there's two sort of canonical examples of these classes of BSM models. The first one is where you add a new vector particle to the Lagrangian. So this is a dark photon. And in particular, we're going to endow this dark photon with a mass. So Lagrangian of the total photon plus dark photon sector looks like this. We have the usual Maxwell Lagrangian for the standard model photon. Then you have a similar term for the dark photon. Then we have a mass term now with the mass ma prime of the dark photon. And then you're allowed to write down a mixture of the two field strength tensors. There's no reason that that's excluded. This is the so-called kinetic mixing between the standard model photon and the dark photon, with the amplitude of the mixing quantified by this parameter epsilon. So epsilon equals 0 would be no mixing. So the interesting feature that can arise in the context of the CMB here is a resonant conversion process. So as the standard model photon propagates through a cloud of free electrons, say after reionization, it acquires a plasma mass. So this just goes like the square root of the electron number density. And if you put in realistic values for the electron number density in dark matter halos, then the values here come out to about 10 to the negative electron volts. If it so happens that this plasma mass of the CMB photon is equal to the dark photon rest mass, Ma prime, that appears in this Lagrangian, then you can get a resonant conversion between the states. And there's a fun quantum mechanics calculation that's like neutrino oscillations in a medium that you can do to compute the conversion probability, and you get an expression that goes as epsilon squared, where epsilon is the kinetic mixing parameter. Okay, in the second case that we're going to study, the other canonical example of this type of situation is where you introduce an axion-like particle into the universe. So the relevant term in the Lagrangian here is this famous Chern-Simons term that involves a coupling of FF dual from the standard model photon with the axion field A. And if you do the math, this is just E dot B times A. So here you have some ambient magnetic field as the photon flies through. If it so happens that the plasma mass of the photon equals the rest mass of the axion, you can get resonant conversion of the photon into the axion. So the numbers here work out, in this case, for the mass range to be the same. But now the conversion probability depends on both the coupling coefficient between the axion and photon and the strength of the background ambient magnetic field that they're living in. But this is the resulting result that you get for the conversion probability. Okay, so if you want some kind of cartoon that gives you some intuition about what's going on, so we have our CMB photons traveling through the universe. If they pass through a cloud of free electrons, for example, in a galaxy or galaxy cluster, if the number density of the electrons in that cloud is just right, then you can get a resonance where the CMB photons convert into the axion or dark photon, and that leaves a frequency-dependent suppression of the CMB brightness at that location. So you'd see these big or small cold spots in CMB maps corresponding to where you've lost some CMB photons. So some of the input parameters here are obviously the mass of these dark particles, the electron densities in these halos, and for the axion case, the magnetic field strength in the halos. If you want some analog of what's happening here, you got spatially varying spectral distortion in the CMB, which is just like the thermal Z effect, for example. It traces large-scale structure in some sense. And so you could imagine making a cross-correlation of this type of spectral distortion, just like we cross-correlate the Compton Y thermal Z signal with galaxy or weak lensing maps. So the underlying technology here is very much something we can directly import from existing data analysis. Okay, so in a little more detail, here are what the SEDs of these signals look like, which is what gives us a unique handle on them in a multi-frequency CMB data set. So the dark photon one goes like 1 over the frequency. X here is just the dimensionless frequency. And the axion one goes linearly with X. The quantities in parentheses are just conversion between the CMB SED in specific intensity units and in delta T over T units. So here's a plot of these. So in the units we work in, again, the CMB is constant as a function of frequency. The red one here is the thermal Z SED that you might have seen before, which crosses 0 at about 220 gigahertz. The purple curve here is the dark photon case, which goes inversely with X, so it blows up at low frequencies. The axion case is in teal, which increases as you go to higher frequencies. And I've arbitrarily normalized all the SEDs to a value of 1 at 353 gigahertz here. The CIB, which is going to be a major contaminant for these analyses, is in orange. So that looks like a modified black body that increases as you go to higher frequencies. So if you want to extract these signals, you need to have some tool that lets you synthesize multi-frequency CMB data in such a way that you preserve one of these signals of interest while suppressing all the other ones. Fortunately, that's a very well-studied problem. And the tool that we've developed for this is called the needlet internal linear combination technique. There's a code that I and Fiona and others developed over the course of a few years called PyILC, which you can download to do these kind of analyses. This is my cartoon of what we're doing with PyILC. It's a big hammer that you can use for all kinds of multi-frequency component separation problems, and we're going to use it to crush this particular BSM SED extraction problem. So I won't go through the math of the ILC. Many of you probably know it. But this is the tool that we're using to extract these maps. So here are what the results look like. So the first thing we looked at was the dark photon case. So if you just take the Planck data and try to synthesize a map of this dark photon induced distortion, you get these maps up here on the top left. At first, you'd be very excited and say, oh, we're seeing some real signal because there's some very dark purple spots in this map. If you zoom in, you find that those are at the location of massive galaxy clusters, and so you're worried about TSZ contamination that's leaked into your needlet ILC map. So we impose these so-called deprojection constraints that null out the contamination from a variety of additional signals. This is where a lot of the hard work in the analysis lives. We test all of this on simulations to be as robust as possible. And after you do that, you get the final map over here on the right. So we then want to take that map. We're then going to cross-correlate it with a tracer of large-scale structure to get the most sensitivity. And we use these unwise galaxies that have been used for a bunch of these kind of cross correlations in recent years. So this is a huge galaxy catalog with about 500 million galaxies in the full sky. So after you do that, you make these cross correlation measurements. In the interest of time, let me go through these fast. So the upshot is that we detect a null signal. We have to also worry about a residual radio bias, in this case from radio sources. We use an external catalog from the first survey to clean that out. The final results are the open blue circles here, and they're strongly consistent with null detection. So you can then fit theoretical models to this, which we develop in the HALO model, and then extract a constraint on this kinetic mixing between the standard model photon and this dark photon. And that's the final result that's shown here. So the mass range that we're sensitive to for the dark photon is the range I told you earlier, around 10 to the negative 13 to 10 to the negative 11 electron volts. And then the y-axis is the kinetic mixing parameter, which is a dimensionless coupling constant. And our new results are the red region. This is the region we've excluded with this study, and it's about a factor 10 improvement over the previous constraints, the previous best constraints in this mass range. And just to clarify, these types of analyses don't require that the dark photon or the axion comprises the dark matter. It just has to be a term that exists in the Lagrangian. So that makes it very powerful. Okay, we then did a similar analysis for the axion case using most of the same technology. So again, we're using PyLC to extract these maps of a purported axion-induced spectral distortion in galactic coordinates. Here's what this looks like with no so-called deep projection constraints imposed. After you impose the deep projection constraints, you get this map over here on the right. You can see some residual galactic dust that's leaking through near the galactic plane. But when we cross-correlate with these extragalactic tracers, that is not a big bias. So again, we cross-correlate with unwise. In this case, we only were able to get robust results using the unwise blue sample. So this is a sample peaking around redshift 0.6. The unwise green catalog of galaxies peaks at a higher redshift, and the CIB contamination that you get at these higher redshifts is sufficiently large that we were unable to get stable, robust results from the cross-correlation. So the results I'm going to show you are just with unwise blue. So here's the final results of the measurement. So the cross-correlation of the fully cleaned map with unwise blue yields a null detection. These are some example theory curves shown in the colored lines for a benchmark value of the axion-photon coupling constant. You can then propagate this again to constraints on the coupling as a function of the axion mass, covering the same mass range as I showed you for the dark photon. And this is now on the y-axis, the coupling strength between the axion and photon in this Chern-Simons term. So our new results are in red. We've excluded this whole range of parameter space. The best existing laboratory constraints are up here from CAST in blue. There are some other astrophysical constraints that come from studying individual astrophysical systems that are shown here in the lines. One reason I think our results are interesting, I mean, for one, they're very competitive with these other probes, but they're based on a population level modeling of this conversion process as opposed to modeling the conversion in one individual system where you really have to know about the exact properties of, say, the free electron distribution in that system. So I think that makes it a very robust probe. Okay, so that's the final thing I'm going to say about that. We're doing some follow-up work now trying to extend these techniques to the ACT data. So everything I showed you here was just Planck. Obviously with ACT, we can then now do this on small scales and back out some additional constraining power. And so stay tuned for those results in the coming months. So in the final couple minutes of the talk, let me just give you a status update on what's happening with ground-based CMB measurements in Chile. The ACT survey came to an end in 2022. This is the telescope being taken off of the mountain, sailing off into the sunset. It's now located at a university in Chile, just for educational purposes. And at the site, we've now, over the past few years, been constructing the Simons Observatory. So this is a picture of the site as of this summer. So the object in the foreground here is the large aperture telescope of SO. The primary mirror is inside of this box. It's about a 6-meter primary like ACT. And then in addition to the LAT, we have these small aperture telescopes or SATs, which are shown over here. They're inside of these ground screens, sort of like the ACT telescope. And the SATs are designed really to go after the large-scale B-mode signature that could come from inflationary gravitational waves. Okay, so Here's a little more detail. The LAT came online earlier this year. This video that I'm showing you is the installation of the primary mirror of the LAT back in February. I'll let this play for a bit, but don't worry, the mirror was not dropped by the crane. It got in there successfully. Here's one of the SATs. This is what this looks like inside of the ground screen. These are smaller telescopes, as the name suggests. They're roughly half a meter primary and again, optimized to look for B modes. So they're kind of like bicep style telescopes, whereas the LAT is meant to be kind of an ACT style telescope, but inside of this movable structure and designed in such a way that we can pack many, many more detectors into the focal plane than you could have done with ACT. So in addition to our stuff in Chile, there's also the experiments at South Pole, including SBT and BICEP. And then at a higher site close to us in Chile, there's the CCAT Prime experiment, which is targeting higher frequencies. So they want to reduce the atmospheric column, which motivates going to higher altitudes. Good. So Planck has wrapped up. ACT, as of 2022, has also wrapped up with noise about 3 times better than Planck. The plan for SO is that we're going to observe through the mid-2030s, expanding the sky coverage to about 60% of the sky. Here's the footprint up here for the LAT survey. The final noise by the end of the survey will be about a factor of 6 better than ACT. And this includes an upgrade, the so-called Advanced SO project that the NSF has funded, for which I'm the co-project scientist. And that's being installed in the next couple of years, basically adding more detectors to the LAT. We're adding more frequency coverage as well. We're planning for 6 total frequency channels with SO. And also, in addition to the 3 SATs that I showed you earlier, we're building 3 more of those that should be online in the next couple of years with funding from the UK and Japan. So again, here's this picture of what the site looks like. And just to show you that the instrument is online and is working, here's a preliminary, extremely preliminary E-mode power spectrum from the LAT data in cross correlation with ACT. So this is just from 2 of the frequency channels in one of the optics tubes of the LAT. There's no error bars on this. It's super, super preliminary, but you can already see the nice acoustic peaks popping up in the E-mode power spectrum from just a few days worth of data. So we're in the so-called initial science observation phase right now with SO. Everything's looking pretty good, and we should start the full survey with the LAT pretty soon. The full surveys with the SATs have already started as of several months ago. So to give you some benchmark numbers, just to get excited, by the end of the survey, we should improve the sensitivity to this benchmark N effective parameter by another factor of about 3 beyond the ACT constraint. And the sensitivity to the tensor to scalar ratio should be improved by almost an order of magnitude compared to the current constraints from BICEP KEC. All right, so I'm out of time. Let me wrap up. So the first part of the talk, hopefully I've showed you that the ACT DR6 data are very impressive. We did this blind analysis of the primary CMB data, found that lambda CDM, perhaps surprisingly, fits the high resolution E modes very well. Accordingly, we then derived very tight constraints on a number of BSM scenarios that affect the primary CMB in particular. A lot of interesting classes of models that could have been at play in the H0 story appear to be very severely constrained, though I think there's still more parameter space to cover in the coming years. So fortunately, we have much more sensitive detectors now on Sky with the Simons Observatory. So stay tuned for the results from our first year or 2 of data in the coming years with SO. So I'll stop there. Thanks.
Thank you very much. Very nice talk. Do you have any questions? Yeah, Frederick?
Maybe I missed something, but what is the science case for the small aperture telescopes with Simons Observatory?
Yeah, good. So this is a science case that I didn't cover in this talk, so it's totally fair that you might have missed it. But what we're going after with the small aperture telescopes is the primordial B mode signature from inflationary gravitational waves. So I do have a summary plot somewhere in my backup slides. Let me try to find it. So this is a summary plot of both the stuff I talked about in this talk and stuff I didn't. So, oops. So this is the TT power spectrum up here, including ACT, Planck, SBT, etc. The E mode power spectrum, the TE cross power spectrum, and then also what I'm showing here is the B mode power spectrum. So the polarization of the CMB, you can split into this curl-free piece, the E-mode piece, and then a divergence-free piece, the B-mode piece, so named because of the similarity with the E and B modes of electromagnetism. And the B modes are unique because there's no contribution in the primary CMB at linear order from scalar perturbations to the B mode power spectrum. So if we detected this large angle B mode power spectrum, that would be evidence of tensor perturbations, i.e. gravitational waves, for which the leading hypothesis is that they're produced as vacuum fluctuations during inflation. Vacuum fluctuations is the metric. So the BICEP experiment is the leading sensitivity to these right now. The upper limit is well below this value of 0.1. So this quantity R just expresses the ratio of the tensor power spectrum to the scalar power spectrum. The current upper limit is something like 3 or 4%. So the amplitude of the tensor perturbations is at most something like 3 or 4% of the amplitude of the scalar perturbations from inflation. And what we're trying to do is to push the limit on this possible component as low as possible, ideally to perhaps make a detection. There is a contribution to the B mode power spectrum that you're seeing here in the dashed curve, which comes from gravitational lensing of the E modes. And we have detected that with several experiments, including BICEP. ACT DR6 is here in red. We've detected this at a few sigma with ACT, and SBT has also detected this. So this tells you about gravitational lensing, so a lower redshift phenomenon. And what we're trying to do is to try to remove that in the coming years through a variety of delensing techniques, as well as foreground cleaning techniques and higher sensitivity to really beat down the large scale measurements here and try to detect primordial gravitational waves. So that's the science focus of the small aperture telescopes from ESO.
But I thought the restriction on low order multipoles was mainly a question of just how much sky you have.
So this is a good question. So in order to go after these low L features in the CMB, you need both a combination of sky coverage, the patch has to be sufficiently large, but you also need to control the noise properties of your data set on these large scales. So from Chile, it's not really a challenge to cover sufficiently large sky fractions. I mean, the signal here peaks at L of 80, so that's of order a few degrees. So you want to cover at least maybe 1,000 square degrees to have a robust estimate of the power spectrum there. So that's not a challenge. The bigger challenge is to try to suppress the large angle noise or low frequency noise in time streams that comes from the atmosphere. And so the trick that we've developed and other collaborations also have developed is to put these spinning half wave plates in front of the telescopes. So these modulate the incoming signal such that the unpolarized signal gets pushed to a higher frequency in the time stream, and you can then demodulate that in your analysis of the time ordered data in such a way that you deproject the atmospheric component, which is predominantly unpolarized, and only preserve the polarized component. And so far, I can't show you the SO data about this so far, but it looks like this is working pretty well.
Amazing, amazing, great work.
Thanks. Yeah, thanks a lot.
We can thank Colin again. Thank you so much.
Thank you. Yeah, feel free to reach out if you have other follow-up questions.